Very good morning, you all, and welcome to our video lectures on artificial intelligence. Dear students, we have completed three classes. The first one is related to the introduction. In the second one, we have studied about the fundamentals of artificial intelligence, and we also have seen the difference between artificial intelligence, machine learning, and deep learning. Also, we have seen the expert systems and all the fundamental and important things we have covered till now. Today, actually, we are starting exactly what do we mean artificial intelligence and what the syllabus we have to follow and study for these things. So we start right from the beginning. Okay. Now we are going for the very fundamental things, that is the what is the building block or what this artificial intelligence consists of. If you minutely observe, a system consisting of a separate database, some operations and control components is the building block for constructing AI system. Artificial intelligence means we are developing a system or we are building a system. In this system, it is not only that simply a laptop or a computer becomes a artificial intelligence system. For that we need separate database, huge amount of database we have to store there, some sort of operations and control components. So these three constitute the building of this artificial intelligence, or these are the building blocks for this artificial intelligence. Okay, we can summarize like this: a generalized production system play a fundamental role in artificial intelligence. So you come across a new terminology like the production system. So this is the most important thing so far as artificial intelligence is concerned. This is the thing we are going to cover in the next slide. So now let us define what is this production system. We have a very good definition for this production system. The various generalization of computational formalism is known as production system. I told you that to more or less this artificial intelligence is related to this computational part, and here the various generalizations of computational formalism is known as the production system. Then what are the major elements of this production system? The major element of these production systems are the global database, that is number one, a set of production rules. We have to apply these rules on the database, and some control system or control strategy, how to control all the things. Okay, that means which rule you have to select, which you have to apply, when we have to go back, what is the backtracking, all the things we do there in our control system. Okay, these production rules operate on the global database. As I told you that first one is the global database, and these production rules, they work or they operate on this global database, and each rule has a precondition that is either satisfied by the global database or not. Okay, so there is a precondition for each and every rule. That means if the condition satisfied, then it is okay, otherwise it has to roll back or it has to apply another rule. So it's satisfied. If it is satisfied, the rule can be applied. If not, then we have to roll back and we have to select another rule and we have to apply. Okay, so this is the things about the production system. Now application of the rule changes the databases. When once you are applying the rule to the databases, the state of the database changes. Okay, that is the meaning of this thing. It is in one state, then it goes to another state, and the control system chooses which application rules should be applied. That means there are a number of rules. Out of that, which rule is applicable now, which rule I have to apply, that is the job of this control system. Okay, that means the control system chooses which applicable rule should be applied and ceases when the termination condition, that is the goal state, reaches. Because our aim is that from the starting state we have to reach the goal state. What is the starting state? Starting state is the problem what you are going to solve. What is the goal state? Is the solution. So when you reach the solution, what next we have to do? We need not do anything, because already we got the solution. Then the thing is over. You get it now? That is the main thing here. Now there comes a confusion. What is this production system and what is the conventional computation system? What is the difference between them? If you observe here, you can see in the production system, this global database is accessed by all rules. Whatever the rules are there, we are having a set of rules and we select some rules, but all the rules we can apply to this global database. But here in case of conventional computational system, it is the hierarchical organizations of the program. Okay, so this is the just divide and conquer like that. It is just like the hierarchy. We complete one, then you go to another one, then you complete one, then you go to the other one, like that. So really you do. Then the second part, no part of the local, no part of it is local. So this is purely global database, no part is local. And rules do not call another rule. Here it is not possible, okay, in case of production system. But in case of conventional computational system, additions or changes to knowledge base might require extension changes to the existing program and data structures and subroutine organizations. So that is the thing in their conventional. And if you observe the another 2 or 3 points there, the communication between rules occurs. That means one rule can communicate with another. There is no question there in the conventional computational system, and only through global database. And all these things it is only through the global database. The fourth one, the design is modular. That means one upon another we can build it, and any changes to the databases, to the control systems or to the rules can be made relatively independently. That means if you make any change to the database, or then all the rules what are there, they also will be applying to the same database. Okay, so these are some of the differences between the production system and conventional computation systems. Some other points are there, you can refer some textbook. So these are the important things, I have mentioned it here. Now one of the most important thing in our artificial intelligence is the gameplay. Now let us go for the variety production system. The example is the 8 puzzle game. The 8 puzzle game, there is a 3 by 3, there is 9 number of cells are there, just in a tabular form, 3 rows and 3 columns, 3 into 3, 3 3 is a 9. So one of the cell is blank. That means nothing is there. This blank cell only will be moving. Okay. The 8 puzzle, it consists of 8 number movable tiles. So we say the cells as tiles. One tiles are there, and this is 3 by 3 frames, and one cell of the frame is always empty. Here the number does not move. Here the empty space or the empty frame, or the, we say, what is the what we call it as the tiles. One of the tiles, movable tiles, the empty tiles, it moves. So making it possible to move an adjacent number tiles into the empty cells. Okay, so there are number of tiles are there, and there numbering is the 1 2 3 4 5 6 7 8 here, who are adjacent, nearby to the empty space. It only it moves. There are 4 rules are there here. One is up, one is down, one is left, and one is right. Suppose the empty tile is in the extreme right of the bottom, it cannot move to the right and it cannot move to the bottom. Only 2 options are there. It can move to the left hand side or it can move to the up. And the problem is of changing the initial configuration into the goal configurations. That means we are moving from your problem state to the solution state, or initial state to the goal state or goal configuration. So solution to this problem is the appropriate sequence of moves. Then how we get the solution? By performing some appropriate sequence of moves. So if randomly we move, you cannot reach the solution, even if you go for an infinite number of moves. Okay, so there is a proper sequence. In that sequence, if you move, then in the minimum possible move, we will be able to reach there. Okay, to solve the above problem, that is the 8 puzzle program, using a production system, we must specify the global database. 3 things I told you. The one is the global database, second one is the different rules, and the control strategy, which rule you have to select, which rule you have to apply, and which rule you have to roll back, or the all backtrack, all the things. This is controlled by the control strategy. Now transferring a problem statement into these 3 components of a production system is called the representation problem of artificial intelligence. In artificial intelligence, most important thing is that how do you represent. Once you represent the problem, then we will be able to solve it. So for the representations, what we need, I told you, first we need a global database. Second, I told you a set of rules. Then I told we need a control systems. So all the things, all the components, it constitutes the production system, and this we call it as the representations problem in artificial intelligence. Now let us see my initial state. This is, as I told you, is a 3 by 3, 9 tiles are there. The first tile it is 2, second tile it is 8, and third is 3. The second row, first one is 1, second one is 6, third one is 4. The third row, the first tile, the number is 7, second it is a blank, and the last one, it is a 5. Okay, so what we do, you can see this is a blank space or empty space. This space it can move up, it can move left, or it can move right. Okay, so this is the possibility there. And what is the goal state? I want to arrange in a proper order: 1 2 3 4 5 6 7 8, and the blank space would be in the middle. So now our time starts because this is our initial state. This is the global database is given to us. The rule is that we can move this blank space either to the left side or to the right side or to the up side or to the down. And which rule, whether now I say I want to move it down, is it possible to move it down? Because there is no tile in the bottom. So only three possibilities there. You can go to the left, you can go to the right, and you can go to the up. Like that, which rule is applicable there, and applying those rules, whether we are going to reach the goal state or we are going away from the goal state. So these things will be controlled by the control strategy. Okay. Now we are going to solve this 8 problem. All of you be attentive and listen me. In this 8 puzzle, each tile configuration is a problem state. So if you see the frame, there are 3 by 3 9 number of tiles are there. Okay. So each tile configuration, because all these 9 configuration changes from one state to another state. Okay. So this state we call it as a problem state, and the set of all possible configurations is the problem space. So two things are there. One is the problem state and another is the problem space. Okay, this arrangement of the tiles we call it as a problem state. It is unique for a particular state, but when you go for a combination of a number of problem states, we call it as a problem space. Okay, here there are factorial 9 different configurations are, because 9 number of tiles are there. So factorial 9 different configurations is possible. So if you go on moving this factorial 9, you can see this much of move it, then it is horrible to find the solution. So what we have to do, we have to apply our control strategy. Using this control strategy, which move is the best one, that we have to decide, and you have to move. Then in a shortest movement, we can reach the goal state. The initial global database is the description of the initial problem state. What is the initial problem state? This is my initial problem statement, or in this initial state. Okay, and this is my goal state. Okay. Then what is telling? The initial global database is the description of the initial problem state. What the number configuration I have to given in the initial state, that is the initial global databases. I told you that whenever we apply the rules, the database will be changing. Okay, that you can understand. Now a move transforms one problem state into another problem state. Okay, that means when you move, the elements get disturbed, so it moves to the next state. Okay, so 4 moves is possible. Move empty space to the left or to the up or to the right or to the down, and these moves are modeled by production rules. Okay, these are modeled by the production rules, and these rules have preconditions that are must be satisfied by a state description. To move the blank up, the blank space must not be with the top row. Suppose it is in the top row, suppose the blank space in the top row, it cannot move to the top, so that is the condition. Okay, suppose the blank space is in the left side, so it cannot move to the left. Suppose the blank space is in the right side, it cannot move to the right because already in the extreme border. Similarly, the blank space is in the bottom, so it cannot move bottom. It is not possible because it is already in the bottom. Clear? These are the things. Then the control strategy, the selecting of the rules and keeping track of those sequence of rules already tried. Because suppose you applied a rule and you could not reach the goal state. If you go on doing the same thing repeatedly, it is foolishness, because the same mistake you are repeating again and again. So you must keep track. This rule already I applied, I could not reach the goal state, so I should not apply it now. So selecting rules and keeping track of those sequences of rules already tried and the database they produced constitute the control strategy. In most of artificial intelligence applications, the information available to the control strategy is not sufficient. It is not sufficient to permit selection of appropriate rules. So see, there will not be rule, because when we created this problem state and we are going for the problem space, we have to create our own rule and we have to apply these rules one by one. Okay. So artificial intelligence production system characterized by search process in which rules are tried until some sequence produces the database satisfying the termination conditions. What is my termination conditions? 1, 2, 3, 4, 5, 6, 7, 8 should be in the sequence number, and in the tiles, and the middle should be a blank space. This is my, so if it is satisfying the terminal condition, then we reach the goal state. That's all. Okay. Then what are the kinds of control strategy? There are basically 2 type of control strategy. One is the irrevocable, another one is the tentative. The rule which is selected and applied without provision for reconsider later on, we call it as the irrevocable. That is not recoverable. We cannot recoverable. Okay. So once you apply a rule, select a rule and applied without provision for later on, you cannot consider, because I don't have a memory, I don't keep anything record of that one. Second one, the tentative. An applicable rule is selected and applied, but provision is made to return later to the point in the computations to apply some other rules. This is the backtracking when we study in details. Suppose I applied some rule. In some cases, there is no provision to roll back and apply new rules. That is the example of irrevocable. But in case of tentative, we can apply a rule, and if we are not reaching the goal state, we can roll back or we can go back to the previous state, and there we can apply new rules. So that you remember. So two kinds of control strategy. One is the irrevocable, second one is the tentative. Now, irrevocable, we need not do anything because it is applied only one time. If it is not reaching the goal state, it is gone. Then we focus on this tentative control. Tentative control, again, it is of two types. So one is the backtracking, second one is the graph search. Okay, two types of things are there. One is the backtracking, second one is the graph search. So suppose a rule is selected and the subsequent computations encounter difficulty in producing a solution. That means we are not going closer to the solution, we are going far away from that one. That means we selected a wrong rule. The state of computations reverts to the previous backtracking point where another rule is applied. That means we did a mistake, we understand that is a mistake, we roll back to the previous step, there only we apply some other rules, that is the backtracking. Okay. The other one is the graph search. These are things we are discussing under the tentative control of the control systems. Okay. Then in the graph search, the provision is made for keeping track of the effect of several sequences of rules simultaneously. So in the graph search, there is a provision. Simultaneously, we can apply several sequences of rules. So that is the graph search. It is not one by one. Simultaneously, we can apply a number of things. Okay. So trial and error methods seem to be inherent in solving puzzles. And one of the most common example of the use of the local knowledge to construct a global solution is hill climbing process. I think this is another topic we'll be discussing about what is this hill climbing. So this local knowledge is useful for constructing a global database or the global solution to the hill climbing processes. At any point, we proceed in the directions of the steepest gradient, that is the local knowledge, to find eventually. That means what you see. Suppose just like a hill, one up direction it is there. It is just like, say, suppose it is like this. It is there. Suppose it is the rising, and it is the downward position, and it is the top level. So we are a position here. Then we are going to another position where we are going closer to the solution. Then we can shift to this one. Similarly, we can go to this point, and finally we can reach this point. And after that, it is closing down. It is coming downwards. Okay. So this is the principle in the steepest gradient in our hill climbing. That is another video by me, that you can refer that one, or you can refer some good textbook for this steepest gradient. Okay, either by the Richard Knight or Nielsen or some other standard books you can follow. So at any point we proceed in the direction of the steepest gradient, the local knowledge, to find eventually a maximum of the functions in the global knowledge. And for this knowledge of the direction of steepest gradient is required. So knowledge of direction is required. In which direction I have to go in the right direction, or I have to go in the wrong direction. If you are going wrong direction, then you are going away from the solutions. That means you can never reach the solution state. Now, let us come to how we go for a solution of these things. Suppose this is my goal state. My goal state is that I have to find the frame consisting of the tiles like 1, 2, 3, 4, 5, 6, 7, 8, and middle the blank space. But my initial state, the global database, my problem state, it is given 283.164, something like that it is given. Now, this is the state is given, and these are a number of problem state, which we call it the problem space. We have to move the tile up and down or left and right, and we go to some other states, and we have to use the best one, the best move, so that in the least possible time or in the least number of moves we can reach the goal state. You can see I have reached the goal state. The goal state here means 1, 2, 3. Here also let's say 1, 2, 3. This is 8 blank 4. It is 8 blank 4. Here 7, 6, 5. Here it is also 7, 6, 5. Then what is my initial global database? This is my initial global database. What is my rules? My rules is there. This blank space I can move it up, or I can move it down. Sorry, I can move it left. I can move it right, or move it down. What is the say limitation? Limitation is that you cannot move it down because you are already in the bottom layer. Okay, in the bottom tiles. Okay. Now, what is the possibility? What can I do? So there is a possibility I can move it up, or move it left, or move it down. So now there are some heuristics that we will study afterwards. while you are going for the searching. Using these heuristics, we have, that means at this point we are having three possibility. What is the possibility? One, you can move to left, one you can move to the left, that means 7 will come here, blank space will go there. Another possibility there, we can move up, that means 6 will come and blank space will come there. Another possibility there, we can move to the blank space to the 5 and 5 will come here. So in this way, out of this 5, which has the minimum heuristic, that we select. So these are the minimum heuristic, because we are not covering the heuristic now. That only I am giving an example how to understand. When I explain this heuristic, that I will explain all these parts there. Okay. Now, if I move this point up, that means the blank space is moved up and 6 has come down. Similarly, now the blank space, when I moved up in my next move, so 8 has come down or blank space has gone here. Then what I am doing? Then making the blank space left, that means 2 is coming here and blank space is coming here. Then moving the blank space down here in this state, what will happen? 1 is coming here, 1 is coming here, 2 will be automatically already there, 3 is there, so it will be a blank space, 8, 4, 7, 6, 5, all the things it is coming there. Now what I have to do? I move this blank space to the right, that means 8 comes here, so finally you reach this state. Okay, so it is 1, 2, 3, 4, 5, 6, 7, 8. Now these are not the only state available. So applying this state or these rules, you can reach there. I told you that there are factorial 9 possibility of moves are there and configurations are there, and there are 4 rules for each and every state. Okay, but what is the best rule? Based on this heuristics I applied and I reached the goal state. So this is the explanation for these 8 puzzle games. Now the function of the state descriptions, the negative of the number of the tiles out of place in compared to the goal state. Say I come to here again. I come to here. Sorry, it is not coming here. I go to the previous slide. Now we come here. See, let us compare this tile and this tile. What is the first number of this tile? It is 2. It is 1. That is a mismatch. So here it is 8 and here it is 2. That is mismatch. 2 mismatches there. Count. So here it is the third mismatch. Here is the third mismatch. Okay. And here also there is the fourth mismatch. Okay, here is the fourth mismatch. So in you understand what I am telling, that here it is 2, here it is 1, there is a mismatch. Here it is 8 and here it is 2, there is a mismatch. 3, 3 it is okay. Here it is 8 and 1 is a mismatch. Okay, so another thing, that here it is a 6, here nothing is there, it is a mismatch. So there is 4 number of mismatches there. So I write the heuristic is 4 here. Similarly here there are 3 mismatches, I write 3. So I write -4, I write -3, because I told you that I use the minus of that one here. The function of the state description, the negative of the number of tiles out of place in compared to the goal state. Okay, so these things, the hill climb methods can have multiple local maxima, and by applying rule to the initial states, if lowers the value of HC function, in this case the initial state description is in local maximum of this function. So regarding this hill climbs, I will take one more classes and I will explain in complete. Then we are going for the backtracking. Applying an inappropriate rule may prevent or delay the success termination. Success termination means reaching the goal state. Okay, that means say, I say one example. Say you have to cook food. For cooking food, you have to put the bowl containing all these food item on the heating. That means on a stove which is burning. But instead of that, if you are putting this bowl containing this vegetable and other things inside a fridge, food will not be cooked, because you have taken a wrong decision. You have selected a wrong rule. For cooking we need heating, but you are putting inside the the refrigeration. Suppose for making ice, I have to put it inside the refrigerator, but I am putting it on the fire. So it will evaporate, it will never become ice. You understand? So applying an inappropriate rule may prevent or delay success and termination. So you may not reach the goal state. So in this case, we try a rule. If it is inappropriate, go back and try another rule. So this is the concept of backtracking. That means there is a provision. If we find it is a wrong rule, we are away from the solution, we roll back to the previous state and we select some other rule other than the rule what we applied 9 to go to the wrong state. Okay. So if inappropriate rule is forgotten and again selected, it further delays the terminations. Okay. So now it is important, when we selected a rule, we have to remember, because if it is a success also, we need the successive movement to reach the goal state in the minimum movement. Similarly, if it is a wrong thing also, we have to remember, because second time we should not apply this wrong rule. Okay, that is the things here. Now these are one of the example of backtracking. Okay. Now I go for this thing. Suppose my thing is there, that is the my initial global database was this one, the tile configuration 283.164.75. Okay. Now I go to the second state. What I have done, I moved the blank space to the left. That means 7 came. Remember, I am just moving it to the left. Okay, it came here. Then should I again move this to the right? Because it is a repetition of that one. Because initially it was blank and I shifted to the left side. If you again bring it to the right, you are repeating the same mistake. There is no result for that one. So what is the possibility? You can move it to up. When you are moving it to up, then what is happening? So 1 is coming down and the blank space is going up. Now again you are here. Now what is the possibility? You can move it right or you can move it up. So I am moving it up. That means the blank space is here and 2 is here. You got it now? Now this is the state. Similarly, if I move the blank space to the right, so 8 is coming here, blank space is coming. That means 8 blank 3 2 6 4 1 7 5. Okay. Now what is the fifth state? The same state I copy and paste it here. This is here. Now what I do, again I move the blank space to the right. When I am moving to the right, so 3 is coming here and blank space is going here. Now what I do, I move the blank space again to the left. That means I am repeating the rule. Because here instead of coming back to the bottom, I am moving to the left side, because it was in the left side, I have gone to the right and again I am moving to the left. So it is a repetition. So what I backtrack, that means I don't select these things, I reject this one, then I roll back. Where I have to roll back? I have to roll back to my previous state. My previous state is here, 8.3, all the things is there. Then what is the possibility? I have to do it there here now. Now what I do, I make it again down. If I make it down now, the blank space, then 834, it is the blank space. Okay. So if you see your previous cases, okay. So then what you do, because it is also going away from these things, this case is already existing also. So this is we have to backtrack, you have to go back, then we have to roll back to the previous state and I commit here again. Then what I do, again I move the blank space to the bottom. When I move it bottom, 6 goes up and comes here. Okay. Then again what I do, I move it to the left side. When I move to the left side, so it become 863, all the things it become. Okay. So if you see here, this is again also a repetition of the previous states. Okay. So it is also a repetition of the previous states. So in that case, what do you do? We roll back. So here the purpose is that, forget about the accuracy of all these things. What I want to tell you that you select one rule, you applied that rule, and by applying that rule, if you are going to a new state, it is closer to the solution, it is okay. If it is showing the previous state again, that means it is repetition. It is because using that I could not get a solution. Again you are applying that one. So this is the problem of backtracking. Okay. And the last one, because these are the things we are studying under the control strategy and control system. Under the control systems, I have told you two kind. One is the backtracking, another is the graph search. Backtracking just now we studied. Then we are going for the graph search, or we say the tree concept. For keeping track of the effect of several sequence of rules, that means at a time I apply several sequence of rules and I remember all the things. So graph search is the best thing. So what is the things I do is here. In the graph search, what I do, so suppose this is my start state or initial state, or I can say initial global database. Okay. What are the possibilities there? I can say, I told you that I can move it up, this is the first case. I can move it left, this is the second case. I can move it right, this is the third case. So there is a 3 possibility, and these are all represented by a graph search. That means at this point I export all the 3 possible. And here, when it is here, then what is the possibility for you? What is the possibility? You can move it up and you cannot move it because the state it was already there. If you move the blank space to the right, this was already the initial state. It is a meaningless thing. Then what I did, there is only possibility I can move it up. So here is only possibility, there is no other possibility. But here again you are having three possibilities. What is the possibility? You can move it left. So 1 is coming here, that is the first case. You can move it right. You can move it right. So that is the 4 is coming, that is the third case. Or you can move it up. So this is 184, it is coming. So this is number 2. That means here by applying the rule, three possible things are there. Here also like this here. What is the possibility? Here the possibility is there. Suppose I move it left side. What will happen? If I move it left side, then it is going back to the same previous state. It is meaningless thing. Then what is the possibility there? I can go to my previous state. Sorry, I can move it up. If I am moving it up, then 4 is coming here. That means here there is only one possibility there. Like that, here you can see there is two possibility. You can move it left and right. Okay. So here there is only one possibility. Only we can move it. Only we can move it down. Why you cannot move it up? Because if you move it up, then it is the same previous state, it is going back. Okay. So like this, you can apply the rules and remember all the sequences, and you can explore all the possibilities. That is the example of a search tree for 8 puzzle program. Then one of the important things we discuss about the traveling salesman. Okay. This is a problem we frequently come across in our university exam also. The thing is that a salesman must visit each of the 5 cities. Suppose a salesman has to visit 5 cities. What are the 5 cities? One is Japan. He is not going to China because Corona is there. The second is New Delhi, and the third one is Moscow. Fourth one is United States. That is your I can say California. California is my favorite city, so it is California. So I am going for the 5th city. That is I am going for Berlin, German. Okay. These are the 5 cities he has to move. A salesman must visit each of the 5 cities only once, and there is a flight between each pair of cities, and the distance is given from this city to that city, that city to that city, and starting at any city A is Delhi. From New Delhi you have to start because you are in India, and you have to visit all these cities only one time. Only you have to come back to Delhi. That means you started from New Delhi and you have to come back to New Delhi. And the problem is to find a route of minimal distance that visit each of the cities only once and return to A. Okay, that is my problem domain. Now I put it like this. I am starting from A. So A to B, suppose this 7 means this is 7,000 kilometer. A is not 7 unit I have given. Suppose A to B, that is 7,000 kilometer. B to C, again 7,000 kilometer. A to C 7,000. A to D 10,000. C to D 5,000. C to E 9,000. And D to E 6,000. And B to E there are 10,000. So what are the cities? The cities are A, B, C, D. Here A, B, C, D, E, 5 cities are there. Okay. Now starting from this city, that means we started with the city A. So A to B is 7,000 kilometer. A to C it is some 6,000, and A to D is 10,000. This is 13, like that. What is the minimum? So minimum is 6,000. Okay. So we have to select AC. Similarly, we explore all other things. What is the minimum? ACD, and again ACDE, again ACDB, then ACDBA. So this is the solution for the graph trapping, and we have one class now online classes. The same thing will be repeated. So I request you all of you to join the online classes also. Till then, goodbye, and thank you for watching this video, and take care of health, and do some online courses. Thank you all.